Excuse me. Okay. We are recording, so we're ready to go. Can you hear me, Olivia, and see my screen and everything?
Yeah, I can.
Excellent. All right, well, let's get started. I don't remember where we were, but we'll figure that out here eventually. Looks like we're on chapter 10. Did we finish up chapter 9? All right. Well, let's see what chapter 10 is all about. Yes. Angular momentum, which means that we have a test soon as well. Let's see. We do have an exam next week, chapters 6 through 10. The exam has, I don't know how many questions. Let's take a look. There are 14 questions, pretty evenly spaced throughout the chapters. I think there's at least 2 questions per chapter and then a couple extras. Yeah, so if you have any questions about exam chapters 6 through 10, you should ask them within the next week or so. That will be due next Wednesday. If somebody needs to be due next Thursday or Friday, that's fine too. Just tell me. We can push it off if we need to, but try to get it done next week. And let's start chapter 10. The last section. This is really the last chapter where we're going to be talking about specifically about movement, like from one place to another or whatever. But it's more particularly rotational movement, but it is kind of movement dynamics, we can think of it as. We move on after this to we can talk about fluids, we can talk about thermodynamics, we can talk about waves. We've kind of got a choice because we only have a few more weeks left. Let's see, how many weeks do we have left? So we have 1, 2, 3, 4, 5 weeks of class left, and then we have finals week, which I believe is the first week of May. And we should check that too, just to make sure we're doing these things properly. Not really sure where to find that. I think it's at the college homepage. There we go. Okay, so that would be May. Yeah, the finals week is the week of May 3rd through 7th, and you can take your final for this class anytime during that week in the Success Center or wherever at the Proctor. But that means we have 5 weeks left, and so after this week, back to our calendar here. After this week, we have 1, 2, 3, 4, 5, 6, 7 chapters, and we have kind of a choice on what we want to do. We can actually cover them all by covering 2 chapters a week for a couple of them if we want to. But we can also just drop a couple of chapters. I think that for people that are going into medical type of careers, it's a good idea to look at the fluid sections, fluid chapters 11 and 12, because there are quite a bit of applications in those things. And then the temperature sections, probably, I would have to say the temperature sections are the least applicable to most people. Temperature, kinetic theory, and gas laws are the least applicable, but some of them are quite interesting. So maybe we can talk about just the first chapter of that and kind of just cover the next couple just for fun, just kind of cruise through them really quickly. And then we could go on to waves and hearing, which again are useful for people going into medical fields sometimes. So I think unless somebody has a different opinion on how to go about this, I think that after we're finished with chapter 10 and our test next week we'll cover fluids, and the week after that we'll cover fluid dynamics. Then the week after that we'll cover all three of these chapters kind of at once: temperature, heat, and thermo. We'll mostly cover this first one, but we will talk about these next two just in passing. We won't really do any homework on them. We'll just do the homework from the first one. And then we'll skip to the wave chapter and do the hearing chapter last. Anybody have any objections to that at the moment? No? Okay, well, if you do later, if you think about it and think that you'd rather cover a particular chapter 14 or 15 more than 16 or 17 or 12 and 13, whatever, just tell me and we can accommodate. I think that will be the most useful and most interesting for us. Now, another question that I want to ask before we're done here in this class, because I think I've asked this before, but I can't remember. Do any of you need to have second semester of this class for your continuing education? No, not particularly. You're not sure? You're kind of looking off? You don't think so? Okay. Well, if you do, I can teach it over the summer if any of you need that. I sometimes get students who need the second half of this class, which covers electrical, magnetism, light and optics, and other things like that. Also modern physics. But if you do end up needing it, I can teach it over the summer, and I have taught it over the summer for people. So. All right, so let's get started. Going back to chapter 10. Okay. Rotational motion and angular momentum. So in this chapter, we're going to use some of the stuff that we've already learned about rotational motion, and we're going to expand on it and talk about kinematics in rotational motion. Kinematics being just like what it sounds. We're going to have a bunch of equations that help us to solve for different things, just like it did in linear kinematics back in chapter 2, I think it was. And then also, we're going to have dynamics. So we're going to deal with forces in rotational motion. And then we're going to talk about energy in rotational motion. So rotational work, kinetic energy, and so on and so forth, potential energy even. And then we'll talk about angular momentum, and then we'll get into some collisions, two-dimensional collisions, gyroscopes. We'll talk about a few things here. So there's a great picture of a tornado. You gotta love tornadoes, especially when you live in tornado country, right? Obviously, there's rotational motion related to tornadoes. Believe it or not, it's not what you think it is necessarily. But let's go ahead and talk about this. So, earlier on, we talked about rotational motion, and we actually were able to define things like delta theta, which is the change in angle as you rotate around a circle, right? And we also were able to define the angular speed or angular velocity. So angular velocity is delta theta over delta t, so that's how much you're rotating in time. Also, we were able to talk about the motion along the edge of a circle, the tangential velocity as it relates to angular velocity. So if you're on the edge of a circle at a constant radius like this, and you're moving around and around, rotating around and around with some delta theta and delta t, delta time, then your omega is related to, or your angular velocity is related to your linear velocity on the edge of the circle, which we sometimes call the tangential velocity, as the inverse of r. So you have an inverse relationship of r with omega and v, or v equals r times omega. Either way, it works out. And all of these things are things we've talked about before. We can also define angular acceleration. So if the angular velocity changes, if omega is changing, in other words, if your rotation is increasing, your rotational velocity is increasing, so the rate of your rotation is increasing, then you can have angular acceleration. Also, if it's decreasing, you can have angular acceleration. So angular acceleration, we're going to define using alpha. This is an alpha, not an A. This alpha will be equal delta omega over delta t. And so here we have a bicycle wheel. We have a person who puts their bicycle wheel upside down, their bike upside down. If you've ever seen that, they don't have a picture of it here, but they should. But anyway, put your bicycle upside down so it's sitting on its seat and its handlebars so that your wheels are free to turn. And you start the wheel spinning by cranking the pedals a little bit. And you're doing it from rest, so the angular velocity is 0 to begin with, and a final angular velocity of 250 RPM in 5 seconds. So essentially you have an initial velocity and a final velocity, and you have a time. And you can calculate delta omega by taking the final minus the initial velocity, angular velocities. The initial angular velocity is 0, so final minus initial will just equal the final angular velocity in this case, which is 250 RPM in 5 seconds. But RPM is not standard. We don't use rotations per minute. We use angle per second, and angle is measured in theta, or measured in radians rather, so it's radians per second. So if we want to change rotations per minute to radians per second, and we've done this before as well, we have to multiply revolutions per minute or rotations per minute, however you want to say it, times 2 pi radians per revolution, then times 1 minute for every 60 seconds. And you can see here that the revolutions will cancel, and you can see also that the minutes are going to cancel. So we're going to get radians per second when we do all of this math. 250 times 2 pi divided by 60 ends up being 26.2 radians per second. So when we plug that in to calculate alpha, delta omega is 26.2 radians per second divided by the 5 seconds that it takes to accelerate that wheel. You get 5.25 radians per second squared of acceleration, angular acceleration. Excuse me. Then in part B, they say that we're going to slam on the brake, and there's going to be an angular acceleration of negative 87.3 radians per second squared of angular acceleration, right? So that's how much it's going to slow down. How much time is it going to take to stop? Well, that goes into place of the alpha, which we solved that previous equation for delta t, and then we plug in that 87.3 in for alpha. Negative 87.3, in fact. And then we do the delta omega on top. Well, the delta omega this time starts at the final velocity is 0, and it begins at the previous angular velocity, which was right here, 26.2. So it goes from 26.2 to 0. So you take 0 minus 26.2, and you get a minus 26.2 over negative 87.3, which gives you a positive 0.3 seconds. And that is the angular acceleration. Pretty simple stuff. Now you can also have a tangential acceleration if you have an angular acceleration that is related to, let's see, where do they do it here? So that is going to be related to your angular acceleration. You have a tangential acceleration, angular acceleration, tangential velocity, angular velocity. So your tangential acceleration is going to be equal to your angular velocity, your angular velocity times r over delta t, which is your change in velocity over t. Now, if that is completely due to, if your tangential velocity is only due to angular acceleration, then it ends up solving out for this right here, where your tangential acceleration equals r times your angular acceleration. And so you can solve that any way you want. You can rearrange the equation. So now we have 3 equations. Now, and these 3 equations are quite important to remember. Let me put them on the screen here for you. We have this one right here, where you take the tangential acceleration, which is the linear acceleration along the edge of a circle. So if you're moving along the edge of a circle like this, and you have some tangential velocity, and you also have some tangential acceleration, which would be pointing also tangential to the circle, but it could be the other way if you want it to be tangential. But you also have some tangential distance that you move here, right here, which would be, we usually call, along the edge of a circle, we usually call that S or something like that, whatever it is, tangential distance. Each one of these tangential quantities is related to the angular quantity, this rotational thing at the center. So the S is related to delta theta, or just theta, you can say, it's fine. So you can say that S is equal to R times theta. That's the distance that you move along the edge of the circle. And you can say that the tangential velocity, your speed at the edge of the circle, is equal to R times omega, angular velocity. And then your acceleration along the edge of the circle, your tangential acceleration, is equal to R times your angular acceleration. So all of the tangential stuff, all of the stuff along the edge of the circle, is equal to the angular stuff times R. It always works out that way. And that actually comes directly from the definition of pi. This right here this comes directly from the definition of pi. This equation comes directly from this one, and this one comes directly from this one. So it all comes directly from pi. Why is this the definition of pi? Because if you go around the entire circle, then our S is equal to the circumference of the circle. And the circumference of the circle would then be equal to R times the angle. Well, if I go all the way around the circle, that is going to be equal to the, that's going to be equal to the entire amount of angle you go around for the circle, which is R times 2 pi. That's the total amount of angle in a circle. And that tells us that the circumference equals 2 pi R, which is the definition of pi. That actually, if you want to define pi from here, you essentially solve for pi. And pi is always equal to the circumference of a circle divided by 2 times the radius of the circle, which is the diameter of the circle. Circumference of the circle divided by the diameter of the circle is the definition of pi. So that's where it all comes from. It all comes from, it's actually kind of amazing, because not many things there aren't many things in the universe, really, in physics and any science, really, that can be proven for sure, that are absolutely true as far as we can tell. This is one of those things. Almost everything else is based on some kind of a guess, or some kind of we're kind of assuming things to be true. This is just measurement. This is just measurement. So as long as circles are, as long as you have a perfect circle, you can define pi to be the circumference of that circle divided by the diameter of that circle. And all of these things follow directly from that. All right. So here's another example. We have a motorcycle wheel that's going to accelerate. Now this brings into our idea, this brings into our experience now, how this relationship of the motion along the edge of the circle is related to the rotation of the circle itself. So if you're riding a motorcycle, then the distance that your wheel moves, or the distance that something moves on the edge of your wheel, is actually related to how fast you're going, as long as your wheels aren't skidding on the road. In other words, I could actually I could spray some paint on the bottom of this wheel right here, and I could let it roll forward without slipping or skidding, and the paint would hit the ground here, and as it rolls all the way around and hits the ground again, I could measure the distance on the ground between the 2 paint spots, And the distance between the two paint spots would be equal to the circumference of the wheel, right? And so you can also say that the tangential velocity along the edge of the wheel is equal to the velocity of the motorcycle moving forward. And you can say the tangential acceleration along the edge of the wheel is equal to the acceleration of the motorcycle moving forward. So this is where we relate the rotational to the linear movements. So acceleration tangential on the wheel is equal to the acceleration of the motorcycle forward, and that's what they're showing here. This is and this is related to the angular acceleration by r. If you multiply angular acceleration by r, you will get that tangential acceleration. So they're telling us that a motorcycle can accelerate from 0 to 30 meters per second, and that's going to be equal to our tangential acceleration in 4.2 seconds. So what is the angular acceleration of the 0.320 meter radius wheels? We happen to know that the tangential acceleration equals delta v over delta t. And so we go ahead and plug those numbers in to calculate the tangential acceleration. It's 30 minus 0 over 4.2, and 7.14 meters per second squared is our tangential acceleration. Now, we plug that into the equation that relates the tangential and the angular acceleration to calculate angular acceleration. We divide that tangential acceleration by r. We get 22.3 radians per second squared of angular acceleration. What does that mean? Well, for every full rotation, there's 2 pi radians. 2 pi is about 6.3-ish, 6.28 radians. So this is about, if you divide this by 6.3 or whatever, you're going to get, 3 something. So this is 3 rotations every second. Well, it's a change of 3 rotations every second. So it's increasing by 3 rotations every second. And that seems reasonable because motorcycle wheels are going around pretty quickly. Now here they actually show you the table of relationships that I showed you, but they show you the other version of them. They show you going from linear to angular, and I showed you linear to angular. But they show you going from linear to angular. I showed you angular to linear. Yeah, whatever. Doesn't matter. But notice that they don't use S here. They're using X, and that's fine. They're just showing a linear version of these things, and that's totally fine. Excuse me. Now, kinematics of rotation. This is one of the first kinematic equations we learned when it comes to linear motion. Well, what if we apply that to the linear motion on the edge of a circle that's rotating with a tangential motion? Then the velocity will equal r times omega. The initial velocity will be r times omega naught. And the acceleration times time will be r times alpha times time. Well, look, every one of these has an r in it. We can actually divide by r and get this equation. Omega equals omega naught plus alpha t. Guess what? That is the same exact equation as this one right here. These two equations are the same. The only thing that's different is we've replaced v with omega in both of them and a with alpha in both of them. Other than that, the equations have the same exact form. So if you want to calculate the final velocity, angular velocity, and you know the initial angular velocity and the angular acceleration, you can do it with this equation. But you can also go back and forth between these equations, because if you divide each one of, or if you multiply each one of these things in this equation on each side by r, which you are allowed to do in mathematics, you're allowed to multiply both sides of an equation by r. So if you do that, then you have this equation. So you can use either one, turns out. And it turns out it's true for all of the kinematic equations. So here are the basic kinematic equations for linear motion. This one is the most basic, of course, which is that the position, or you could say distance, equals velocity times time if the velocity is the average velocity. So distance equals average velocity times time. These 3 equations all require that you have a constant acceleration, and these 3 equations all require that you have a constant angular acceleration. So if you have a constant acceleration, linear acceleration, then you have final velocity equals initial velocity plus acceleration times time. You have a final position or distance, you could say again, because this is final position minus initial position. I prefer the version of this equation that looks like this. Delta x equals, because that's actually true, because this should be x final minus x initial on this side. But anyway, equals initial velocity times time plus 1/2 acceleration times time squared. And then this one should also be a delta x here, just so you know. Should be distance or displacement. Final velocity squared equals initial velocity squared plus 2 times acceleration times change in distance or change in position or the distance traveled. And it turns out that for angular stuff, the equations are the same. We have total angle that you travel through. And so each one of these would be deltas on either side. Total angle that you travel through is equal to the average angular velocity times time. The final velocity, angular velocity, equals the initial angular velocity plus the angular acceleration times time, assuming again that we have constant angular acceleration here. Then the final, the total amount of angle that you rotate through is equal to your initial angular velocity times time plus 1/2 times the angular acceleration times time squared. And then the final equation is that your final angular velocity squared equals your initial angular velocity squared plus 2 times alpha times your change in theta, delta theta, change in angle. And it's always important, I think, to remember that in these equations, you have these conversions that you can use. You have a conversion that you can go from x to from theta to x by multiplying by r. X equals r times theta, and you can go v equals r times omega, and you can also do acceleration equals r times alpha. So maybe in some questions that you're given or problems that you're given, you might be given a bunch of linear stuff and you want to change it into angular. Or maybe you're given a bunch of angular stuff, you want to change it to linear. You can do that. Or maybe you're given a mixture of each, and then you can change some of it over to linear and use the linear equations to solve your problem. Or you can turn some of it into angular and use the angular equations to solve your problem. You can use either set of equations to solve problems. It's not really one or the other. You can choose. Sometimes it's easier to do one than the other because they've given you more information. If they give you more information in the angular realm, maybe it's easier to use the angular equations. If they've given you more equations in the linear realm, maybe you go that direction. You also have this relationship here, which is the way to calculate the average velocity, initial velocity plus final velocity over 2, and you can do the same thing for angular. Sometimes those are included with the kinematic equations. But let's do an example now. Here's an example where we have a deep sea fisherman that catches a fish. And here is the situation. Here is the fishing reel. And this fishing reel is going to be rotating. Let's see what it says here. Okay, the fish is swimming away from the boat, so it's pulling the fishing line from the fishing wheel. And the whole system is initially at rest, and the fishing line unwinds from the reel at a radius of 4.5 centimeters from the axis of rotation. So it's a really good idea to start labeling things right away in problems when you're doing this, because it can get really confusing. They're giving us a lot of stuff. So this 4.57 is or 4.5 centimeters is a radius, and so I'm going to label that with r equals 0.045 meters. That's a radius, and I want to remember that it's a radius. So I'm going to just circle it there. There's an angular acceleration. An angular acceleration is an alpha, and that's 110 radians per second squared. They've given it in the correct units, so we can just write that down in the correct units without converting. And then they give us a time of 2 seconds. That's also in the correct units, so we're good to go. First thing they want to know is what's the angular velocity of the reel? Well, angular velocity is omega, and that's omega final, so it's just omega like that. Well, one thing that we know is that from rest, it says right here, initially at rest, that means omega 0 equals 0. We're trying to find omega, but omega 0 is equal to 0. So one of the first equations that we have been given in the kinematic equations is that omega final equals omega initial plus the angular acceleration times time. Well, that equation can be used to solve this. We have omega initial, we have angular acceleration, we have time. And then they say, what speed is fishing line leaving the reel after 2 seconds elapses? Well, when they're talking about the speed that it's leaving the fishing reel, they're talking about this right here. We are measuring how fast the line is coming off. This is a linear thing. This is a XVA kind of thing instead of a theta omega alpha kind of thing. And so what, in part 2 and part B, they want to know what is V. Well, in part A, we actually calculated omega already. We calculated the angular velocity, and the angular velocity is going to be related to the speed that the line's coming off, because the line is originally rotating around the reel and then it comes off the reel with that same relationship. So we use the relationship between linear and angular. Linear speed equals r times omega, which is angular speed or angular velocity, and we multiply the radius times the solution to part A. Once we've done that, we get 9.9 meters per second. Now, does that seem reasonable? 9 meters is about 30 feet, 35, 30, yeah, it's about 30 feet actually. 9.9 meters is more like 34 feet or something like that. 33 maybe. So that's 33 feet per second. That's actually moving really fast. 33 feet is like the length of this room. Can that happen in a second off of a fishing reel? Yes, it can, especially with deep sea fishing. If you catch a big fish like a shark or a tuna when you're deep sea fishing, you can definitely have your line pulled out at 30 meters per second, 30 feet per second. If you're ever deep sea fishing and that does happen to you, I recommend you pour water on your reel, because your reel will heat up very quickly at that speed. But it can happen, especially with sharks and tuna. They are very fast moving fish. Anyway, so that's definitely good. In part C, we're going to find the number of revolutions. So we know the angular velocity, we know the linear velocity, we know the final angular velocity, the initial angular velocity, we know the angular acceleration, we know the time. We can do this because one of the equations will give us that with all those numbers that we have. We plug in all the numbers into the second kinematic equation for angular stuff, and we get 220 radians of rotation. They want to know how many revolutions. For every revolution, there is 2 pi radians. So we divide the 220 radians by 2 pi radians, and we get 35 revolutions. So 35 revolutions of the reel in 2 seconds. Then they want to know the number of meters of fishing line. Well, if we know the number of radians, we know theta, we can find out x, which is the number of meters. It's just r times theta. Turns out to be 9.9 meters. So we can definitely use these equations just like we used kinematic equations. You're just going to pick the equation that has the thing that you want using numbers that you already have. Here they're going to slow down the fishing reel using a fishing reel brake. And the brake is going to give it an angular acceleration of negative 300 radians per second squared. We're going to find out how long it takes to bring it to a stop. We're going to use this kinematic equation, which is the first one. We're going to rearrange it to solve for time. We already have the initial and final. The initial angular velocity is 220. The final is 0, so it's final minus initial. And then we also know the acceleration. Plug it all in. It's 0.733 seconds. Here's another example where we do this. We have a train accelerating from rest. It has 0.350 meter radius wheels. Again, I would just label these things. This is a radius, so r equals 0.35. And then here they have an angular acceleration again. That's alpha equals 0.25. And then after the wheels have made 200 revolutions, well, 200 revolutions are a theta. They're an amount of angle or amount of rotation. So that's 200 revolutions, but we need to convert that into radians, and there are 2 pi radians per revolution. So I'm going to do that conversion really quick. That's going to be so they've given me a theta, they've given me an R, they've given me an alpha, and they want to know how far does the train move? Well, when you multiply this out, you'll get theta, and how far the train is going to move, it's just going to be R times theta. That'll be part A. Part B, what's the final angular velocity of the wheels and the linear velocity of the train? Well, that's going to be a kinematic equation and a conversion. So in part A, they just use this conversion from angular to linear. They multiply R times the theta that we have, and they get X. They first do the conversion, and then they convert to radians, or they convert to linear, 440 meters moving down the track. In part B, they're going to use the last kinematic equation to solve for omega final. When they do that, they plug in all the other stuff that they know, omega initial, and the acceleration, and the theta that we got from part A, and they get 25.1 radians per second of final angular velocity. Now to find the final linear velocity, you just multiply that angular velocity that we just calculated by R, which is the 0.350 meter wheels. You get 8.77 meters per second of velocity moving down the tracks. Here they do another one where they're calculating the distance traveled by a fly on the edge of a microwave plate. That one's pretty straightforward. But the bottom line is that the kinematic equations in rotational motion are the same as the kinematic equations are in linear motion. The only difference is that sometimes you'll need to convert things into the correct units. You go from revolutions, for example, to radians per second, or revolutions per minute into radians per second, or revolutions into radians, or something like that. And also sometimes you might have to change over from angular to linear or linear to angular, because they might ask a question, how far did it go, which is a linear question, and you maybe only know how much it rotated, which is theta, an angular thing. So you might have to convert theta into X by multiplying by R. And that's the only real difference between the two. Okay, so before we get on to the next part, let's see, how many sections do we have in chapter 10? Looks like 7. Yeah, before we move on to the second part of this, I want to take our little break here. We'll take a break for 5 minutes, come back at 15 after. I'm going to go get a drink, wet my whistle, and then we'll come back and we'll talk about rotational dynamics. Okay, now we're ready to go finish up this. We won't quite finish this chapter today, I don't think. Maybe we will, but my guess is that we'll probably still have 2 sections to go when we're done. Maybe at the end here, but we'll see. And then we'll just finish those Thursday and also answer homework questions. Also, I haven't, so the labs that we've done so far cover everything up to rotational motion, but there is a new lab for rotational motion, by the way. So lab, let's see here. I want to say it's lab 6 maybe. Yep. So in lab 6, you're going to do a yeah. So yeah, in lab 6, you're going to roll your IO lab thing here, and I found they use cardboard rolls. I'm not sure what they're talking about when it talks about cardboard rolls. Like, is that like from a big tube that you mail posters in or something? I can't figure it out, but I don't have anything that's the right size for that. But I did decide that if you can find a can, like an old coffee can or something like this, and then put the IOLab in it, right in the center of it, and stuff like newspaper around it or something to keep that thing in the center, as close to the center as possible, then it works pretty well. It also works with, like, if you buy like a 28-ounce can of, if you have an old 28-ounce can of tomatoes or something, that works. A fairly big water bottle would work if the IOLab would fit into it, or a jar of some kind if it's round. But in this particular lab, you're going to need something to allow it to roll in, and they're using this weird method that I cannot figure out how they did it. They just happen to have the right size roll or something of, cardboard, tube of cardboard or something. But a can works just fine, and it doesn't even have to fit all the way in it. If the IOLab sticks out on one side or both sides a little bit, as long as it's pretty centered in the middle, so that the mass is distributed nicely and in the middle, about the middle axis, that works. Because what you want it to do is you want it to rotate around the axis that goes down the center of the IOLab. And the reason for that is because right in the center of the IOLab, there is an accelerometer, which can measure rotation. And so when you do this lab, you will be measuring what we call the moment of inertia, which is what we're about to learn about. So in this one, you're actually going to figure it out yourself. You're actually going to figure out how to measure it yourself. And so we're going to talk about what the moment of inertia is, and you should be able to figure out how to measure it from that. And then you're also going to figure out the math for calculating it by yourself. And then you're going to do this. You're going to, when you figured out how you're going to measure it and how you're going to calculate it, in other words, what experiment you're going to do, and then what you're going to do with the numbers of that experiment to actually calculate the moment of inertia. Then you will actually do that experiment. You want to do it several times over and over again, the same way every time, so that you can actually average all those numbers together and get a good minimization of your error. So that lab doesn't have step-by-step instructions. It just has what you're supposed to accomplish written here, and then you go out and accomplish it. As a result, you will write up a report, a page or so long, telling me what you did, what the actual action, the actual activities that you did, the numbers that you took, the data that you took, the calculations that you made, and your results. you have a table of data and some written down calculation somewhere. So this might end up taking a couple of pages if you have a lot of calculations and a lot of numbers a lot of data that you took. But so this one is a little bit more kind of on your own activity than the previous ones.
I have a question about the grade book. Do you enter these lab grades into the MyOpenMath, or
Yes,
do you enter them somewhere else?
no, I will enter them in by hand in MyOpenMath. Unfortunately, I haven't gotten around to doing that because I hate entering grades in by hand, but I will get around to it. I'm sure that you're worried about what grades you're getting on those labs. As long as you completed the lab, did the activities, you're going to get probably an A on the lab. I'm not a big stickler for specific things in labs. I just want you to get some experience and learn some physics firsthand. So you don't need to worry too much about those as long as you've completed the work and turned it in.
Okay.
If you are really worried about one in particular, I can go and look at it, and I will get around to that. I spent all of my spring break doing hand grading for another class. I'm just tired of it and trying to take a break from it for a little bit, but I will enter those in eventually. Yes.
Okay.
And the ones that are in MyOpenMath right now are a little bit different titles than the ones that I've been giving you, because as I've mentioned, this is kind of my first year using these IO labs, and I'm still kind of converting my classes over to the use of them. But the Lab 6 activity is the one that you want to download, the PDF or the doc file, either one, and then you can do that lab. Now the next lab on the list is, let's see, the next lab is for wave motion. So we're going to have a rotational motion one, and then that's it for that. I don't think that I haven't figured out a way. Well, I have figured out a way to do some fluids labs with the IO lab, but that's going to require that I build some detectors or convert some detectors that I already have so they can be used with IO lab. And I have not done that yet. That will be a good several months kind of project for me. And I'm pretty sure I haven't found anybody else who's done this already, so I'm going to be inventing it on my own. So anyway, we probably will not do any fluids labs. Well, we will do some, but we won't do any with the IO lab. We'll be using different things, probably household items, to do our fluids labs and gas labs with gases. So anyway, that's just a heads up. We will be doing some labs here in the next few weeks, but they will be more based on finding things at home to do the activities with. All right, so moving on to 10.3. In the dynamics of rotation have all of the same features of the dynamics of linear motion. When I mean dynamics, I mean the study of the forces that are involved. So forces that cause accelerations, for example. But also not only that, but the laws of Newton, the laws of physics, Newton's laws in particular, are also valid here. There, for example, there is such a thing as rotational inertia. Remember that linear inertia was this thing that causes things to keep doing what they're doing already. So if something is already moving in a constant velocity, in a constant direction, it's going to keep doing that unless you force it to turn or force it to stop or whatever you're going to force it to do, force it to speed up. You have to actually add some force to it. And that is also true with rotational things. Things will continue to rotate unless you cause them to stop rotating somehow. You have to apply some kind of a force to them or cause them to change their rotation somehow. And that actually has some really interesting consequences. And also, if you want something to accelerate its rotation, if you want to speed up the rotation, slow down the rotation, you have to apply a force. There has to be forces involved. And that's Newton's second law. Of course, Newton's third law is that there is an action for every reaction, or reaction for every action, I guess. And that is also true in rotational motion. So all these things, all these laws of physics are still obeyed, but how they're obeyed is a little different because it is rotation, and rotation is just a little more complicated than linear motion. So if we say that force equals mass times acceleration like Newton did, then we convert the acceleration, which is a linear thing, into angular acceleration. We have to multiply angular acceleration by r, and we get this equation: force equals mass times radius times angular acceleration. Well, we also know that torque is the thing that causes forces to cause things to rotate, right? So when we talk about forces causing rotation, we usually talk about torque, because it's not just the force that matters, but the distance from the center of rotation, which is r in this case. So if we multiply the left side by r to make it a torque at a 90-degree angle, then we multiply the right side by r because we multiplied the left side by r, we get this equation. And this equation says that torque equals mass times r squared times the angular acceleration, right here. And this starts to look a lot like Newton's second law. Newton's second law is this law right here: force equals mass times acceleration. This law is torque equals this thing times angular acceleration, where this thing is m times r squared. Well, if we replace this m times r squared with something, then we can create an equation that looks very similar to force equals mass times acceleration for rotation. Instead of force equals mass times acceleration, we're going to get torque equals something times angular acceleration. The something we're going to call moment of inertia. Torque is going to now equal moment of inertia times angular acceleration. So this is the analog. Remember, we've got a lot of analogs going on, things that are analogous, right? This is analogous to force equals mass times acceleration. Here we have linear acceleration. Here we have angular acceleration. Here we have force. Here we have the thing that causes angular acceleration, which is torque, right? Here we have mass, and here we have this thing called I, which is called moment of inertia. And I, for a single particle, a particle mass, is equal to the mass of the particle times the distance that it is from the center of rotation squared, mr squared. So these two are analogous. Remember, we have all these other analogous equations, like we have x equal, or so delta x rather, change in x equals omega. Not sorry, I'm getting things all mixed up. Velocity times time. We also have delta theta equals omega times time, right? So these two are analogous. This is the angular version. This is the linear version. These two are also analogous. This is the linear version. This is the angular version, right? This would be net force here. So this is like Newton's second law. This right here is like Newton's second law for rotation. If something is accelerating, then there is a torque being applied. The net torque is equal to the acceleration times the moment of inertia of that object, where if that object is a single point particle, it's like a point particle like this with some mass m, and it's rotating around with some angular acceleration alpha, right? And it's some distance r from that center of rotation, then this I here is equal to mr squared. And why is it that I keep saying that? Why is it, do I say if it's for a point particle at a distance r? Well, because it's different for different shapes of particles or different shapes of objects. For the simplest shape, which is a point particle at some distance r, it's a very simple calculation to calculate the moment of inertia. The more complex the particle, or the more complex the shape that's rotating, this gets much more complex. And the mathematics of that is well beyond the scope of this class, but let's take a look at it anyway.
We're not going to look at the math. We're going to look at the results of the math. So if you had a bunch of these particles, a bunch of point particles, and you lined them up in a long ring so that they connected around an axis like this at the center, then that actually has the same form of moment of inertia. But you just take the mass of all of those particles combined, which would be the mass of the ring or the mass of this hoop, and multiply it by the radius of the hoop squared, and that would give you the moment of inertia of a bunch of particles all lined up at the same radius. So that kind of makes sense. However, if you have a thickness to your hoop or your ring or a cylinder, turns out it works for a cylinder as well. This also works for a cylinder, a long skinny. So as long as the cylinder has no thickness to it, it works. And that would be a hollow cylinder, not a solid cylinder. But if you have an annular cylinder, which is essentially a ring that has some thickness to it, so it has an inside radius, radius 1, and an outside radius, radius 2, and some thickness in between, and filled with mass, then you have to take into account both radiuses, both radii in Latin, by taking their squares and adding them, and then dividing by 2, which is essentially an average. If you have a solid cylinder, then you take the radius of that cylinder, multiply by the mass of the cylinder, and divide by 2. And it turns out it doesn't matter what the length is. The moment of inertia is just the mass times the radius squared over 2. And that's if you're rotating it around the center axis here. Notice that all these things show where the axis is. What if we rotate it, instead of rotating it around the center axis that goes down the center of the cylinder, we rotate it around an axis that goes through the cylinder from the top to the bottom of the cylinder like this? Then it has a very different moment of inertia. M, the mass of the cylinder, times the radius squared over 4, plus the mass times the length of the cylinder, because this time the length matters. The longer this gets, the harder it is to get it spinning. So that's mass times length of the cylinder squared divided by 12. And this is where we start to get a feeling that the geometry matters. The geometry really plays a role in how these things rotate. And what is this moment of inertia talking about anyway? The moment of inertia essentially tells us how easy or hard it is to get this thing rolling, to get it going, to get it rotating, right? So if you have a bigger number, then it's harder to get it rolling. If you have a smaller number, it's easier to get it rolling. In general, the more mass that you have that's far away from the axis, the harder it is to get it rolling. So in this case right here, a hoop at about a cylindrical axis, all of the mass is at the farthest distance away from the center, from the axis. So this kind of thing is much more difficult to get rolling than this kind of thing, or this kind of thing, or even this kind of thing. This is one of the hardest things to get rolling, just a hoop of mass some distance r away from the center. All other things being equal, this is very difficult to get rolling. These things are easier to get rolling. What if we have, instead of a cylinder that has some radius to it, what if it has very little radius? In other words, it's a very skinny rod, a thin rod, and it's rotating about its axis. Well, in that case, it turns out that this part with the r doesn't matter, because if the r becomes very, very small, this becomes much, much smaller even. And so that part goes away, and we just get the length of it times the mass, the length squared times the mass divided by 12, just get the second half of this part. And what if we rotate it, instead of rotating it around the center of it, we rotate it around one end, kind of like swinging a bat? Well, then it's just ml squared over 3 instead of ml squared over 12. It turns out that this one is easier to get spinning than this one, because if the mass and the length are the same on these two, you divide this one by 12, you get a smaller number, so it's easier to rotate. This one you divide by 3, which is a bigger number, and so it's harder to rotate it around the end than it is to rotate it around its middle. Ask anybody who's twirled a baton if that's true, and they'll tell you that it's true, because twirling a baton about its middle is actually very easy to do, whereas twirling about its end takes considerably more effort. And then a sphere. So if you have a solid sphere and you're rotating it about anything that goes directly through the center, any line that goes directly through the center, and you're rotating around that axis, it's 2 times m times r squared over 5. So it's actually a fairly small moment of inertia. fairly easy to get a sphere rotating. If it's a shell, in other words, a hollow sphere, like a ball with air in the inside, then it's 2 times m times r squared over 3. So you're dividing this one by 3, dividing this one by 5. This one is a smaller one than this one. So a hollow ball is actually harder to get rolling than a solid ball if the masses and the radiuses are the same. Here we put a hoop. We're gonna rotate a hoop now, but instead of rotating it around an axis that goes through the center of the hoop, we're gonna that goes right through the middle of the hoop rather without touching the hoop. We're gonna rotate it around an axis that goes through 2 sides of the hoop and goes through the center of the hoop. And it turns out that that's mr squared over 2 compared to this one, which was just mr squared. So it's actually easier to rotate it this way. It's kind of like putting a ring on a table and then spinning it, on the edge of the ring. That's much easier to do than it is. It's twice as easy to do than to rotate it around the axis going through the center. And here we have a rectangular slab rotating around its center here. And this one is fairly complicated. You have the side squared added together times the mass divided by 12, moment of inertia. So those are a bunch of different moments of inertia for different shapes. And of course, if you have something very complicated, let's say, for example, a person which has all kinds of weird shapes to them, can be very complicated and have a very complicated moment of inertia. So when you have, for example, a ice skater who's rotating on their skates, right? As they're spinning around on their skates, they can actually change their shape. So they can change their moment of inertia. They can stick an arm out or 2 arms out or their legs out or whatever else, and then they can pull them all in really tight, or they put them above their head. They can change their shape at will, and therefore change how easy it is for them to rotate. So let's take a look at some examples of how you would deal with this moment of inertia thing. So here we have a person pushing a merry-go-round on the playground. And this was one of my favorite things to do. We would get out there with like 5 people and get this merry-go-round going so fast with somebody in the middle getting sick, and then they get out towards the edge and they get even more sick. So much fun. But when they get really sick, you have to get away from the merry-go-round. Anyway, there he's going to exert a force of 250 newtons at the edge of the 50 kilogram merry-go-round. That means there's going to be a torque applied there. The force, you got a distance, you got an angle of 90 degrees, you can calculate that torque. The radius is 1.5 meters, so they're telling us that. We want to calculate the angular acceleration produced when no one is on the merry-go-round. So we know that torque is equal to moment of inertia times acceleration. So we can calculate the acceleration from that if we want to, or we can calculate, or let's see, they actually, yeah, so we're going to use that equation in part, at the end of part A here to calculate the acceleration. But we need to know the torque, which we don't know yet. We have to calculate that. And we need to know the moment of inertia, I. So the torque is equal to the force that the man is pushing with times the radius of the merry-go-round, because he's pushing at the edge of it. So he's pushing at that distance. And then the sine of the angle between them, which is 90 degrees. So sine of 90 degrees is 1. So you multiply these, you get 375 Newton meters of torque. The moment of inertia, we're going to assume that this merry-go-round is a solid disk. And the solid disk rotating around the axis going through the center of the solid disk is 1/2 mr squared. So we can calculate that, 1/2 mr squared, 56.25 kilogram meters squared of moment of inertia. Plug those into the equation, Newton's second law for rotation. Get 6.67 radians per second squared. That means that we're accelerating this at 1 rotation every second. So if we do this for 2 seconds, it will be going 2 rotations per second. If we do it for 1 second, it'll be going 1 rotation per second. Because this is just over 2 pi radians, right? So it's just about 1 rotation per second, a little bit more than 1 rotation per second, which is a pretty fast rotational acceleration, but doable. I could definitely see that happening. You couldn't maintain it for very long before the thing was spinning so fast that it was out of control, but you could do it for a few seconds maybe. Then we have, in part B, we're going to calculate now what happens if he does the same thing. He applies the same amount of torque But now we're going to add a child on here. So we're going to put a kid right here at some distance from the center, hanging on, right? And this distance is going to be different. The distance to the child is going to be a different distance. We're going to call it big R. And the child has some mass. Now we're going to consider this child to be a point child. The child will be like a point mass. And if you remember when we added things together like masses, we just added them together. Well, it turns out with moments of inertia, you can add moments of inertia together if they're rotating around the same moment, the same axis. Since the child is going to rotate around the same axis as the merry-go-round, hopefully if they hang on tight anyway, then we can add them together. So the moment of inertia for the child can be calculated separately and then added to the moment of inertia for the merry-go-round. And that's what they do down here in part B. The moment of inertia for the child is going to be mr squared, which is the moment of inertia for a point particle, where I'm a point child here. 18 kilogram child, 1.25 meters distance. Square that, multiply them together, get 28.13 kilogram meters squared of moment of inertia for the child. The sum of those two is going to be the total moment of inertia. It turns out to be 84.38 kilogram meters squared. And then we put them back into the equation to solve for alpha. Torque, which is the same amount of torque, same man, same force, same distance. And then the moment of inertia is different, and we get 4.4 radians per second squared, which is less than we had when we were just pushing the merry-go-round, which we would expect. We would expect that putting the child on would make it more difficult to rotate that merry-go-round, and it did. Okay, now we can also deal with energy. And again, it's another analogous thing. It's an analogy from linear mechanics. Linear mechanics, kinetic energy. And I can't remember what they call it here, maybe linear, or I think they call it translational or something. So kinetic energy, translational, would be equal to 1/2 mv squared. These are equal to each other. Well, in dynamics, we replaced mass with moment of inertia. And we replaced linear velocity with angular velocity when we went to rotational dynamics. And so we would assume that we'd be able to make a kinetic energy that's rotational. It looks like this, and it turns out it's true. And we can actually demonstrate it. I believe they do demonstrate it here. Yeah, so here they talk about the work equaling the net force times the distance traveled. Well, the distance traveled, if we're going to switch it over to angular, we're going to have to include r. So what we do is we take that distance and we divide by r. That'll give us theta. But if we're going to divide by r, we need to multiply by r on this side as well, or divide by r on the other side. What we're going to do is we're going to actually multiply by r on this side and then divide by r, so it's like it goes away. But when you multiply r times net force, if the angle is 90 degrees, you get torque. So here we get work equals torque times alpha. Sorry, torque times theta. And then torque, which is I times alpha, we can get net work equals I times alpha times theta. And then we can actually use kinematic equation right here, omega squared equals omega naught squared plus 2 alpha theta, to solve for alpha times theta, because we have an alpha times theta up here, right there. And then we can plug this equation in to there, and we get net work equals 1/2 I omega squared minus 1/2 I omega naught squared, which looks just like the work energy theorem, where these are the kinetic energies, and that's where we got kinetic energy before. So kinetic energy equals 1/2 I omega squared, and we are right. And we also have a work energy theorem. So rotational kinetic energy, 1/2 I omega squared. Pretty easy to demonstrate that. Now, what use is that? Well, it's actually very useful. It's used all the time, actually, in your car. Your car has all kinds of spinning wheels in it. And one of the reasons it has spinning wheels is to keep the engine running. The engine can, you can make all kinds of engines that can make things go, that can make things move. But to continually make them move, to make them move over and over and over and over again, it's often a good idea to have something rotating in the engine to cause the next cycle to happen. And that's why so many of our engines have rotating parts in them. It's not necessary that the engine have rotating parts, but it is quite useful because that rotating part will have some kinetic energy, and that kinetic energy can be used to continue the next cycle. All engines have cycles as they go around and around and back and forth and up and down, all these things that they do. One of the simplest ways that this can be done is to actually just put a big wheel inside of a vehicle. So like a school bus or something, you put a huge spinning wheel on the bottom of it, and you get it spinning every morning using electric motors or something, or whatever you want to do. You can put some hamsters on if you want. But if you get this big heavy wheel spinning, it's got a lot of kinetic energy, and then you can actually connect it directly to the wheels of the bus and get the bus moving with that wheel. Depending on how heavy that wheel is, you can actually get the bus going quite well. You can also use that big wheel to charge up batteries, which then can be used to turn motors and turn the wheel, turn electric motors. But there are many other ways that this can be used. I mean, it's really, these are what we call flywheels, and flywheels are used all over the place. On your engine, you probably have 4 or 5 flywheels, maybe at least. One of the things that the flywheels in your car does is it powers the air conditioning system, for example. The other parts of the electrical system are often powered from a generator that has a flywheel on it, and that flywheel is essentially storing some rotational kinetic energy from the engine, from the motor, from the engine in your car that is actually it's actually burning gas usually, and it's converting that motion into that linear motion into angular motion, which is going to then be turned into electrical motion or electrical energy. Here we're gonna have a grindstone, and we're gonna actually slow down this grindstone. I think. Let's see. Yeah, they're gonna apply. No, this person will start up a grindstone, get it started. She's gonna exert a force pushing on the grindstone to get it started, and they can push with 200 newtons through 1 radian angle. So again, I would recommend that you write down things. So we can see here that we have a force. This is equal to a force because it's in newtons. They want to know how much work is done here, and that's linear work. Then they're doing a radians thing here, which is an angle. So this has to be a theta. And then the force is kept perpendicular to the grindstone. So this is a radius. Perpendicular means that the angle between the two is 90 degrees. So you can just kind of put that in there and say that that means that the torque is going to equal to R times F. There will be no sine of theta there. The torque equals R times F. And they want to know how much work is done. They want to know the final angular velocity. Here's the mass that they give us, and they want to find the final kinetic energy, rotational kinetic energy, which is equal to I 1/2 I times omega squared. So we're actually going to have to figure out what I is as well in this thing. So all these things it's good to know what we're using, what we're given, and if it's linear stuff or angular stuff, right? The work is a linear thing. The angle is an angular thing, of course. This is related to torque, so that's more angular. Radius is given there. They want to find the final angular velocity, which is an angular thing. The final kinetic rotational energy, which is of course an angular thing. So we've got some linear things, some angular things. We'll have to do some conversions back and forth most likely. And let's see what we're doing here. So the net work is going to be equal to net torque times theta. So we already knew that we could calculate the net work using torque times theta because they did it right up here. They did it right at the beginning of this derivation of kinetic energy. So this network is usually force times distance, then we made it equal to torque times angle. So that's totally valid. So they calculate the net force using the net torque times the angle. The net torque is R times F. We know that the angle between the R and the F are 90, so we don't have to use an angle there. And then the theta is given as 1 radian. So we just plug in those numbers, boom, boom, boom. 64 Newton meters of net work done, or 64 joules, same thing. And then to calculate the final angular velocity, we can actually use kinematic equation. We know the initial angular velocity is 0, and we know theta. We don't know alpha, but we can calculate alpha because we already know the torque. We calculated the torque up here to be 0.320 times 200 newtons. So that's your torque. And torque is equal to I times alpha. So we can take that torque and divide it by the I. So they recalculate the torque here, but they can calculate the I for a disk. They can consider this this thing to be a disk, so it's 1/2 mr squared. Plug those numbers in, you get this is the I. Then you divide the torque by the I right there, and you get the angular acceleration. Then you can plug that into the kinematic equation to get the final angular velocity. Then the rotational kinetic energy, we have everything we need for that now. We have I, we have omega, we plug them in, boom, boom, done. Here they do another one where they're doing helicopter blades. So the rotor blades, there's 4 of them, they're 4 meters long each, and they have a mass of 50 kilograms. So each one of these are going to be approximated as thin rods, kind of like baseball bats being swung around the end of the rod. When you do that, then you're going to have 4 times that moment of inertia. The kinetic energy is equal to 1/2 times the moment of inertia times angular velocity squared. The angular velocity they calculate they convert the revolutions per minute into radians per second. So that's how they calculate the angular velocity. But the moment of inertia is 4 times the moment of inertia of these thin rods rotated around their ends. So that's the mass times the length, each squared divided by 3. Plug in the numbers. There's your moment of inertia. Then they plug all that into the equation for kinetic energy, rotational kinetic energy, and they get 5.26 times 10 to the 5 joules of rotational kinetic energy. Now the translational kinetic energy of the helicopter, let's see. Yeah, so the translational kinetic energy of the helicopter, you're going to use this for the velocity, 20 meters per second. So in part B, we have 20 meters per second of velocity. So you square that, multiply by the mass, times 1/2, 20 times 10 to the 5, or sorry, 2 times 10 to the 5. So this is essentially, this one right here is 200,000 joules. Rotational is 500,000 joules, more than twice as much energy in the rotating blades as there is in the actual moving helicopter. Right? And then if you use all of the rotational energy of the blades to lift the helicopter up to the maximum height, then you can say that the rotational energy of the blades is all going to become potential energy. So we set those two equal to each other and we solve for the height. 1/2 I omega squared for the rotational kinetic energy, mgh for the height of the helicopter, and this will tell you the absolute maximum height the helicopter can go before it's run out of kinetic energy in its blades. And you solve that, you get 1/2 I omega squared over mg, and you plug in all the numbers, you get 53.7 meters. Not very high for that particular speed of those blades. Okay. So here's an interesting experiment that you can do at home. You take 3 different cans of food that all have the same size can, and then you roll them down a slope. So you can just put a board on a couple of books or something and roll them down the slope. Well, it turns out that if you have 3 different kinds of food, you will actually get 3 different speeds of rolling for these cans. And the reason is because each of the materials in the cans have a different mass, and the mass is actually distributed differently. For example, if you have soup that's filled with a bunch of vegetables in it or something, and you put the can on its side, the vegetables will either float or sink or something, and they will distribute their mass differently in the liquid. If you have something thick in the can, like pumpkin or something, then it's pretty evenly distributed, and it's going to have a different kind of rolling motion because of that. In other words, where the mass is matters, and how much mass there is matters. So, so every different can of food tends to have a little bit different rolling acceleration, angular acceleration going down, because it has a different moment of inertia. Where the mass is and how much mass there is what goes into the moment of inertia of each object. Now, in this particular example of 1010, they actually do a thing where we're going to calculate the speed of a cylinder rolling down an incline. We have a solid cylinder that's rolling down a 2-meter high incline. It starts from rest, has a mass of 0.750 kilograms and a radius of 4 centimeters. Now, they do not show a picture of this, but they should. So let's make a picture of this. So here's our incline. And here's our solid ball, solid cylinder. Not a ball, it's a cylinder. And what are all the forces involved here? Well, the forces involved include the mass being pulled down by gravity, so the gravitational force straight down, right? And then there's a friction between the cylinder and the ground here that's causing it to roll. If there was not friction between here, this ball would just slide down the hill, right? If you've ever been bowling, you may have noticed that your ball, when you bowl your ball, it doesn't actually roll down the lane usually. It usually slides down the lane, and that's because the lanes are slippery. Have any of you ever stepped over the line when you're bowling and noticed that you slip really hard on the lane? Well, it's true. The lanes are oiled. They actually have oil on them that makes them very slippery. So it's oil on, I think it's oil on top of wax of some kind. But the lanes are very slippery at a bowling alley, and so the balls don't actually roll. You actually have to force them to roll. You have to make them roll before they hit the ground, or they will not roll as they go down the alley. And it's the same on a slope like this. If the slope has no friction on it, the ball will not necessarily roll. It will actually slide down the hill more than roll down the hill. And so you have to have some friction here to make this happen. So there is friction here that's going to cause this to roll. So notice that we have two things and two things going on here. Where is this thing rotating about? First of all, the point that this is rotating about is kind of weird. It's actually rotating about this point down here, where it's making contact with the surface. You could pretend like it's rotating about this point in the center of the ball, and it kind of is. You could determine it that way, but either way, it's not. It's moving along as it's rotating, so it's kind of got a weird thing going on there. But here you can see that this force here is not lined up with this point of rotation. This force here is not lined up with this point of rotation. So whichever point you choose for your point of rotation, there is a force that's not lined up with that point of rotation, which means it's going to cause it to rotate. So whichever point you choose for your point of rotation, there's always a force that's not lined up with it, that's not going through that point, that is causing a torque, which is going to cause it to rotate. And that's really what causes a ball to rotate as it rolls down a hill, is either the friction or the weight, depending on which one you consider, what point you consider to be your point of rotation. Okay, so now we have the solid cylinder. It's rolling down a 2-meter high incline. The cylinder starts from rest and has a mass of 0.750 kilograms and a radius of 4 centimeters. You can be grateful that we're not trying to do this using forces, because this is kind of a messy problem with forces. We're going to use energies, which is much easier, because at the top we have a potential energy equal to m times g times h of the ball. So you just take the height of the ball times gravity times mass, or the cylinder rather, height of the cylinder times mass of the cylinder times gravity. And that's the energy it has before it starts rolling down the hill. When it gets to the bottom of the hill, or while it's rolling down the hill rather, it has two kinds of kinetic energy, and it would also have some potential energy. But when it gets to the bottom of the hill, it only has kinetic energy. It has linear kinetic energy, which is the kinetic energy of it moving forward. And then it has rotational kinetic energy of it rolling because of these forces that act on it. So these things we can work out. Now, if we don't know the rotational velocity, and if we want to convert it, we can. And they do that here, because omega equals v over r, which is linear speed over radius. We can just replace v omega squared with v squared over r squared. And then, of course, I we can calculate because we know it's a cylinder. It's 1/2 mr squared for a cylinder. And then we've got an equation that's all linear variables now, and we can plug in the numbers and be done. When we look at this, we notice that we have a mass in each term, so we can divide out the mass in each term. And then we can combine these two on the right-hand side to be 3/4 times the velocity squared, and that's equal to g times h. So if we want to solve for v, we just solve it like this, and it turns out it's not even dependent on the mass. It's 4 times g times h over 3, and you take the square root of that. Plug in the numbers, you get 5.11 meters per second of forward velocity as the ball rolls down the hill. What this really means is, because we're splitting the energy here, we're taking this potential energy at the top of the hill and we're splitting it between forward kinetic energy and rotational kinetic energy. Linear kinetic energy, rotational kinetic energy. That means that something that rolls down a hill ends up moving forward more slowly than something that slides down a hill. And this is quite obvious to people who've been sledding a lot. If you've been sledding on the snow a lot, you know that at the bottom of the hill, you're moving really fast. If you go to that same hill and ride your bike down it, you're not going to be going as fast at the bottom of the hill, because some of the potential energy at the top of the hill goes into rotating your wheels on your bike. And that is a kinetic energy that has to be used to rotate those wheels. And it's not used in your forward motion at that point. So that is that. All right. What are we at here? Still got some time. Okay, the last thing that we're going to talk about is angular momentum now. So angular momentum. Previously, we learned about linear momentum. Linear momentum was equal to, we called it P, and we said it was equal to mass times velocity, and it was a vector. And just like that, we're going to convert into linear momentum, or angular momentum, which we're going to call L, which is also a vector. And we're going to say that it's equal to I, because previously we changed masses into moments of inertia for going from linear to angular. And instead of using V, we're going to use angular velocity, which is also a vector. So angular momentum equals moment of inertia times angular velocity. And we also mentioned before that linear momentum is conserved, and I think that I said something that linear momentum is conserved, but it's not conserved absolutely. It's not actually conserved in all such situations. But it turns out that angular momentum is. Angular momentum is actually one of the few things that is actually conserved forever, completely, absolutely. We have never observed it to not be conserved, and we can't even conceive of a situation where it wouldn't be conserved, as far as I know. And this is actually what is responsible for things like the rotation of the planets around the sun, the rotation of the Earth around its axis. Those things have been happening for billions of years. And the reason they've been happening for billions of years is because that angular momentum is conserved. In order for that angular momentum to be transferred into something else, you'd have to have something like the size of the Earth kind of interact with the Earth. on a very personal basis, like crash into it. And we suspect that that has happened before. Can anybody guess what our evidence is for that something has actually interacted with the Earth by crashing into it, and that momentum was transferred to something else? Can anybody think of something that rotates with the same amount, with the same rotational time as the Earth, and that is like fairly close to the Earth? The moon is what it is. Come on, it's the moon. So the moon actually rotates with the same rotational velocity as the Earth, and that's why we only see the same side of the moon all of the time. Whenever we see the moon, it's always the same side of the moon. The far side of the moon, it never points towards the Earth. And one of the reasons we think that is the case is we think that the moon may have once been part of the Earth. That early on in the Earth's life, something came in and collided with the moon and the Earth and broke off this chunk of the Earth, and it became the moon eventually. And so part of the Earth's original momentum is now being carried around by the moon. And part of it is also probably being carried around by whatever ran into the Earth and the moon at that point, if it's still out there, or if it became part of the Earth and moon, it's now part of the Earth and moon. But anyway, the point is that angular momentum is an absolutely conserved quantity as far as we know in the universe, as far as we've been able to observe. So we're going to calculate the angular momentum of the Earth and see how big this thing is. It's a sphere, it's a solid sphere, and so we're going to use the moment of inertia for a solid sphere, use the mass of the Earth and the radius of the Earth, and plug them all in here, and we're going to get this number that turns out that is 9.72 times 10 to the 37 kilogram meters squared revolutions per day. That's a huge amount of angular momentum. If you do it in meters squared per second instead of revolutions per day, it's 7.07 times 10 to the 33 kilogram meters squared per second. It's the same value, it's just in different units. But it's huge. 10 to the 33 is a big number. Huge angular momentum. Now, just like in linear, angular momentum is going to be related to force. But before, we said in linear stuff, we said net force equals change in momentum over time. So net torque, we're going to change it to torque, and we're going to change linear momentum to angular momentum. So net torque will be change in angular momentum over time. What does that mean for us? That means that if we know the change in angular momentum, we can calculate how much torque was used to do that. So here we know how much angular momentum changed because we know how much the spinning changed. And no, actually we didn't. We know that the force that was applied, so we're going to calculate the change in angular momentum. So we calculate the torque from the force applied and the radius of the turntable and the time that it took to do it, and we calculate the angular momentum by multiplying those things together. There's angular momentum. To calculate the final angular momentum, let's see. What's the final angular momentum of a lazy Susan that starts from rest, assuming friction is negligible, and the final angular velocity of the lazy Susan, given that its mass is 4 kilograms and its moment of inertia is that of a disk. So final angular velocity we're going to calculate from the angular momentum equation, just rearrange it, and we're going to use the original angular momentum that I calculated in the first part A, and then we're going to divide that by now the moment of inertia of the thing. It turns out to be 0.721 radians per second. That's totally reasonable. Calculating the torque from kicking a ball. So in this particular case, we're going to kick a ball. We're going to give it a certain amount of force at a particular distance so that we'll be able to calculate the torque. And the moment of inertia of the lower leg is this amount. We want to find the angular acceleration of the leg from that. Well, that's just Newton's second law. We calculate the angular acceleration of the leg from Newton's second law on the torque. And then the final angular velocity, we can use the kinematic equation to calculate that final angular velocity. Then we can calculate the kinetic energy of the rotation from that, because we've calculated I mean, it's just the same, these are the same calculations we've done before. We're just using angular stuff instead of linear stuff. It's not any different. Nothing new in the math for sure. And then there's conservation of angular momentum. This, if you have a system where there's no external forces involved that are going to transfer the momentum into some other object, then the angular momentum at the beginning is the angular momentum later on is equal to the angular momentum later on or before or whatever. The angular momentum cannot be transferred out of a system unless there's an external force causing it to transfer out of the system into something else. So if that's true, then angular momentum is equal to I times omega. And that means your I times omega to begin with has to equal your I times omega to end with. And this is particularly interesting when you have things that can change shape or change mass or other things like that. The perfect example is the ice skater. So here you have an ice skater with her arms out and one of her legs out, and she's spinning on this one leg. And she has a particular angular, particular moment of inertia like this, and a particular angular velocity when she's like this. When she brings her arms and legs in close to her body, then she has a different moment of inertia because she has a different shape. Her mass is in different distances from the center of rotation, and she'll have a different moment of inertia. Well, what do we observe when we observe skaters like this? What happens when a skater starts out with their arms and legs out and then brings them in very, very close? Anybody know?
Spin faster.
They spin faster when they bring their arms in close. Why is that? The reason for that is because when their arms are out, their moment of inertia is big because their mass is far away from the center of rotation. Whenever your mass is far away from the center of your rotation, your moment of inertia gets bigger. That means that, and this has to be equal to when she brings her arms in and legs in, that means her moment of inertia is much lower. So if she has some kind of moment, she has some kind of rotational velocity here that's, you know, small, and then all of a sudden the I becomes small and these two sides have to be equal, then all of a sudden your angular velocity has to get big over here. And that's where the spinning gets much faster. And this happens in all kinds of things, particularly in sports, but also many other things. But in sports, the motion of the pitcher, if you watch a pitcher pitch the ball, they keep their arm very, very close into their body when they start their pitch. But when they at the end of their pitch, their arms are way far out away from their body. Why do they do that? Because it changes the moment of inertia. And it actually, in that particular case, you're going from here to here, actually. You're going from being able to move it very easily to being able to make it harder to move, but that actually increases the force on the ball, which increases the acceleration on the ball, even though the moment of inertia is lower. Or sorry, even though the angular velocity is lower, the force on it is much bigger. So, I mean, it happened. We take advantage of this in many, many different ways in the world around us. Here, they're actually going to do this this problem with the angular momentum of the skater, and they give us the moments of inertia, you know, for arms in and arms out, and they give us the initial angular velocity and calculate the final angular velocity. If the initial angular velocity is 0.8 and the final is 5.1, then of course you've increased this sevenfold, you know. Not quite sevenfold, a little more than sixfold. Kinetic energy. What happens to kinetic energy though? The kinetic energy of rotation is not conserved. So the kinetic energy when she's moving slow is 29.6. The kinetic energy when she's moving fast is 191. Kinetic energy is not conserved in rotation. So that takes us to the end of 10.5. Now, like I said, I'm going to save 10.6 and 10.7 for next time, just because it's going to take too long to start 10.6 for today. So we'll stop a little bit early today unless somebody has questions on the homework already. That's entirely possible. And questions about what we've done so far. Anybody have any questions for me today? All right, if there are no questions, we will end. And We will see you on Thursday. Don't forget to download the new lab, which is Lab 6. And you should do the soup can experiment. It's kind of fun. Have a soup can race. You can place bets on them with your siblings or your roommates. All right, have a good one.